Okay, guys. Great to see you here this evening. This is the first event for computational AEC group. Um, so we started this group as there wasn't really a group dedicated to computational design in Melbourne. Um, Sydney, Brisbane, Perth have got their own group, so we thought that we can start a group and join the family. And uh, the the way that we are thinking about running this group is to create a atmosphere of sharing and caring for the community. So it's like a four group, by group, for community sort of thing. We like to share our knowledge and I don't know, ideas with everyone, and we welcome any presenters, any speakers who want to share their ideas, their work, and their future with us. Please contact us with the details here. You can contact us on Twitter or through an email or a website, which is a little bit long, but it gets shorter as it goes to the end. Um, so just a few quick things before we jump to the first presentation. Um, We are going to send you updates about future events, like when is the next event and so on. We're going to use the email that you sort of registered to this event. In case you don't want to receive the email, let us know, just to make sure we don't spam you. And also, huge thank you to Swinburne University for allowing to use this facility in this space. Thank you very much. And with that, we can start the presentations. Tonight we have two presenters, Zach and Mehnush. I'm going to introduce Zach and hand in the microphone to him to start the presentation. Zach is an architectural designer with strong focus on technology and their application in projects, actively seeking design quality improvements and team workflow optimizations from an interdisciplinary approach. The key pursuit is to produce evidence-based and scientifically justifiable design solutions with great efficiency. Zach has two professional degrees in architecture and specializes in computational design and digital engineering solutions. Let's start with Zach. This and your presentation. This one.
Thanks. Thanks for joining us, and very excited to join the first event. And this is a real urban design project, and later derived into part of the R&D project. And I'm from Jacobs. So the topic today will be algorithm-based parametric urban design. And firstly, about myself, my name is Zach. I'm from an architectural background and BIM person, computation designer, also partially works for the digital engineering team in Jacobs, even though majority of my time will be spent in the architectural team. And I consider myself a poor storyteller in terms of architectural design. That's why I took down the way of scientifically design stuff and using data to justify my design qualities. So I'm quite pragmatic and rational thinkers. And I use generally Rhino, Grasshopper, and Rivet, Dynamo, and Node, the APIs, and I do a little bit of scripting in both Python and C#, and also create plugins. Right, so before moving to the actual project, so this is a list of key points or questions I ask myself when I work on any architectural projects. So what is a good design? I'll put my focus on 2 points, quality and efficiency. And traditionally, what I observed is that people design stuff based on their experience plus their feelings. So it's more based on an intuitive approach. And I would suggest design things from a more scientific approach in order to make sure you know what you want at the end of the day. So I've broken them down into a few longer questions. So what are the ideal outcome? That will be the goals in this kind of logical thinking in computational design. And how to measure the level of success? That will be the benchmark. And what constraints and what resources available? Those will be the inputs or adjustables or parameters. And what are the logic behind the decisions? And this will be the most critical one as it forms the main algorithm. And these 4 points are the main kind of considerations when we started this computational design project for the urban design. All right, so first section will be a quick comparison between the urban fabric in terms of roads, street types, and designed by designers from an intuition way, and also the algorithm generated design outcome. And it's not really about which one is better, but it's rather a comparison between the two, and for us to have a good understanding of why there's a difference and what can we adopt from each side. So this is the urban design project we worked on, and this is a basic network connection. So this is the first step we figured out, and later we give them a categorization of different street types for them, so as represented in different colors. And then the third step will be assign a specific width to each street type. For example, the widest, the main street or the main road will be 60 meters wide, and the narrowest will be roughly 6 meters just for single lane and pedestrian access. In each of the slides, majority of the slides, I'll put on these inputs and kind of keynotes for you to refer to. For example, in this case, we have the basic road layout, key locations, so these diamonds here. The largest one is the city center, and that's the town center, and these are the neighborhood centers. And once we got the results, I've run a test against the connectivity from these key urban functions like the city centers and town centers, and generated a heat map, basically represent which road is heavily used and these blue paths are not very much used, so they become less busy, and bring that information into changing or optimizing the road width. So that's the result in green. So if you look at left and right, it's actually quite different. There's a huge difference between design by intuition and also algorithm generated outcome. Obviously, we're not taking this for granted and say this is the most ideal solution. That's not the case because there's other factors, but at least that highlights the difference between when we think we need the road to be constantly wide across this whole side, while when you measure the connection, you really don't need the road to be that wide. Obviously, we need input from especially specialists from different disciplines like road designers, but this is just one example. At the same time, when a road type and width changes, the data is also getting updated. So this is mainly about the NFA, net developable areas of the blocks enclosed by the road network. So just briefly, a concept about the computation design. It's of the application of computational strategies to the design process, while designers traditionally rely on intuition and experience to solve design problems. And computational design aims to enhance that process by encoding design decisions using a computer language. It's really not competing against the traditional way of design. It's rather deconstructing the existing logic and enhance it by the computation power. So this is a workflow of this urban design project that we adopted. So we've already covered the road networks and the key urban locations. So those two will provide us with the traffic density pressure testing, and that will also provide optimization to the road hierarchies. And when the road hierarchy changes, the building will be relatively influenced because of the developable area is changed as well. And then the second part is building scoring and metric assessment. So these two will be basically to provide a score for each building relative to its connectivity or accessibility to all kinds of urban functions. So that comes from the input of road network, key urban locations and buildings. And also because this project was and completely built on Revit. So we have a nice BIM model with all the information embedded for every single building, including the category, the type, usage, estimated number of apartments, estimated number of population or dwellers in each of them. So overall, they'll be able to provide a metric assessment against, for example, we want to put a school somewhere when we're aiming to cover 75% of the residential communities within that area. So this is the metric assessment we're running. And this whole process is a recursive process, basically cycling itself until we told it to stop, until we pick the ideal result we want. And two parts about this project, quality and efficiency, as I mentioned in the very early beginning. We have functions of parametric city planning and traffic assessment and database city function coverage study. So this is about improving the quality. That's something the human brain cannot simply just can't do it, no matter how much time, how much resource being invested. And for the efficiency part, rapid road network and building prototyping, BIM data exchange management, this is more of speeding up the workflow. You can still do it traditionally, but it just takes heaps more time. So there are two key concepts used in this urban assessment. So the coverage, I think that, well, there's one key concept. So going through the whole project, the coverage is of, it's more of a walkability or traveling distance. And in this map, we have these square blocks as urban functions, and the diamonds are small buildings. So traditionally, when people design something like, for example, a station, and they do assessment of the surrounding coverage, and let's say want to do a coverage of 300 meters, and traditionally people draw a circle, use that point, with a radius of 300 meters. But we all know that's not the case, because the real coverage is going to be a lot smaller, really depending on, for example, the complexity of the road fabric, or how complex it takes to travel from point A to point B. So the real result will pretty much be a irregular polygon that we don't know. But that actually makes a huge difference to urban design. So this is a demo of how the real traveling distance is calculated. For example, we have an urban function with a design coverage of 600 meters. And these white lines with number tag are showing essentially the actual traveling distance from this dot to the central urban function. So for example, here it's 521 and it's 487. And it spreads out. Obviously, you don't have coverage here because that's a lake, and the only connection across the lake will be through these three bridges. And bring the same concept to multi-points. So we have coverage of 600 and two small centers with design coverage of 400. And it's the same concept applied to multiple urban functions. So I'll quickly show two animated videos. So that's basically a traveling simulation from the center to the end, and same concept from multiple urban locations. Then back to the this urban design project itself. We brought in the BIM data and linked that function with the coverage testing model. So essentially, in this example, we have this a local town center here with a design coverage of 1,000 meters of traveling distance, and the end of these red curves are pretty much showing the end of 1,000 meter traveling. And then these buildings in different colors are representing, for example, the green one would be medium density apartments, and blue one is single family houses, and also shows the coverage, the percentage of service covered by this local town centers. And you may notice there's a bunch of houses at the corner there that isn't covered by this town center. So the solution for designers would be either you can move this town center up, or alternatively, you can add another town center or increase the coverage, design the coverage capability, or change the road layout to provide better connections. Now, all those inputs, again, needs to be checked with the respective specialist, because, for example, you can't have a urban facility design if you have a 5,000 meter coverage if you expect people to walk towards the center instead of driving. So similar concept. So 4 neighborhood centers turned on with a 400 meter of coverage each, and this is showing the percentage of coverage, and for community centers as well. And finally, if you have all the functions turned on, that's going to provide obviously 100% of coverage, but normally you don't do that because they belong to different categories, and that's something I'm going to cover later. All right, so later this kind of workflow derived from the original project into an R&D project. So we seeking to replant it to something else, to any other urban design project. So I use the Melbourne CBD as my testing field. So this picture here contains 420 million times of calculation. It's lots of calculations. And there are 2 key concepts used in this scoring system. So this is about score. Each building with different color would have a score. Obviously, the red color is a better score, and cold color, the bluish one, is a low score there. And there are 2 key concepts. One is proximity. The other one is betweenness. Proximity primarily used to identify the level of accessibility from the urban element to key urban locations of a single category. So, and then betweenness is to multiple key urban functions with weighted considerations. So my analogy would be getting a milk. So if you live close to a Coles or a 7-Eleven, you can get a milk from either place. So as long as you live close to one of the supermarket, whether it's a big one or a small one, you get a nice score for proximity. While for betweenness, it's more for the purpose of someone seeking to buy apartments in the city and where they're going to live. So for people who commute a lot, they might prefer live close to a train station, interchange. And for cultural lovers, they might prefer live close to a Melbourne Museum, for example. So there's different priorities being set in between these testings, and this is really about what sort of project you're designing and who are the customers you're targeting. So getting the concept visualized, it's the same map. Betweenness, so these buildings, because it's close to one of the urban functions, so these 3 buildings get really good proximity scores, and that one has the poor proximity score because it's not close to anything. But at the same time, for betweenness, this building actually has the best betweenness because it has an average nice accessibility to all of these surrounding urban functions. And this is a simulation on Melbourne CBD. I've put in currently 5 stations: Melbourne Central, Flagstaff, Parliament, Flinders, and Southern Cross stations. And I've arbitrarily set the coverage settings to 400 each. And this is showing the 400 meter coverage in the CBD area of Melbourne. So actually quite different from what we expected by drawing a circle of 400 radius. And again, if I increase 3 of the stations to 800 meter coverage, and it's going to show a bit of difference. So it looks like fried eggs. And later, if we increase Melbourne Central and Flinders to 1,500 meters, it's going to even cover the north part of the CBD and a bit of the South Bank. But obviously, again, 1,500 meters is probably too much because normally if your station is away beyond 5-minute walk, you're going to lose at least 50% of your passengers. So that's not ideal. Again, all these inputs will be checked by the specialist from each discipline. And also it provides a bit of density testing, as I mentioned in the beginning. All these curves in colors are representing how busy the road is potentially. It's basically a calculation of when you do all these commuting simulations and you have overlap data. If the road is used 100 times, the other road is used 50 times, then the one used 100 times is considered a busy road. And for betweenness, the one big difference is that you have all the data or the heat map overlapped together. So for example, in this map, we have Melbourne Central, Victoria Market, Myer Store, Federation Square, and Melbourne Museum. And they have different design catchment, but at the same time, the current weight is set to 1. So they have an equal priority at the moment. And obviously, the building at the center of kind of average of all of them, would have the best score. So that means living here would have the best quality of life accessing all these facilities. So imagine you design a urban project and you move one of these functions around, and you can instantly get the result of the most valuable buildings. And also, if the priority is being changed, for example, I've set the weight of Melbourne Central and Melbourne Museum both to 8 and 10, 8 and 10, very high scores. So that will result in a shifting towards the northeast part. So just a quick comparison between the previous and the current slide. And next one, and that's another shifting by changing the weight. So I'm just going to quickly show video demonstrations of that. So firstly, this is its application on the actual urban design projects. So when the coverage or the design coverage number grows, more buildings covered. And in the very end, so when it reaches its maximum design coverage, you realize there are still a few blocks of buildings remain in dark blue. So that means they don't really have good accessibilities to all these design functions. So again, the solution will be either change your road layout or move your functions. And this is the coverage we talked about, utilizing the data from Revit. So estimating of how much population is covered and what's the percentage of coverage for each type of buildings across the site when you have these changing figures for the urban function coverage. And this is visualized proximity, those 5 train stations, and that's how they gradually cover up the whole CBD area, but still with different scores, heat map, and that's a visualized Betweenness. So you may realize the heat part shifted from the center to the southern part. Then the last part is the weight shifts. So this is a clearer demonstration of how the reddish area shifts from center to south bank, because I have the Federation Square priority increased. All right, so then some digital engineering stuff, mainly focusing on improving the design efficiencies. So first one is the network generation. Before I joined this project, we have designers manually drawing up the street layout. So each time they change the layout or change the width of the road, they have to jump in the CAD and redraw it. So this is just a little bit of basic but quite smart way of doing things. So we get the network, and then we have assigned this width parameter for each type of the street. So when we update the layout, or when we update the width of them, this whole thing is going to automatically update it. And so that's the result of comparison. So when you increase the width of the 4 types, and that also increase the areas, resulting in either gain or loss in net developable areas. And also the tree placement. This is originally this was created for the Revit modeling, where we want to plant trees. So first we've got the tree information from landscape architect. So they tell us what sort of what's the strata size, what's the radius, what's the frequency of tree being placed for each type of road. Obviously on this model it avoids the intersection of road to keep a clear eyesight. And this map shows roughly 8,700 trees across the city, and I've got everything else turned off in Revit, and these are the trees placed in Revit, basically linking the data with the specially built tree families of different sizes and adjustables to reflect whatever we tested, and all these are done in Grasshopper. Then some more exciting stuff is the automated buildings, because each time when a design changes, the road network changes, road width changes, it's going to make an impact to the developable areas in between. So your building design for the last phase for visualization purpose will no longer fit the updated layout. And not even mentioning, we had a few drastic change around. So that essentially means you have lots of distorted land that cannot fit the originally built buildings. But it's taken a lot of time to rebuild the buildings each time when the design changes. So that's why the strategy we later adopted would be firstly dividing the whole urban site to a series of zone of characteristics. So for example, this is university character zone, commercial and city center, low density residential areas. So let's use the university area as one example. All these orange colored blocks are net developable areas for buildings. And we applied a parameter to divide the grid up to a series of building footprint. And again, the size of it, how many buildings and how you orient them will be determined by the character of the current urban zone. And obviously with a series of chopping the sharp corners, eliminating useless space, and generate them with a series of other parameter inputs. And eventually when the road network changes or whatever changes, all this building will be updated accordingly as well. And also apply another series of parameters for the architectural tectonics and also the facade treatment. So eventually we can get the model. That was done in Grasshopper and a little bit of Python. So because Grasshopper is generally my favorite tool for complex geometries comparing to Dynamo. But we did use Dynamo to pick up those geometries and automatically built them as generic families and place them in the right location and coordinates in Revit. So this is the result in Revit. Because I guess a lot of people might think that Revit is, it's kind of a lot more accurate comparing to Rhino, but it's also, generally speaking, it's slow when updating these complex geometries. But with the help of like the software, kind of connecting different softwares and take the best out of each of them, we sort of achieve this increase the speed workflow. And that's pretty much the end, and just some script. And this is one of the main script used in the Grasshopper, the controlling different part. We've got information imports, core algorithms, Revit BIM data exchange, design visualization, output, traffic testing, and graphic control. So nothing in this slide is Photoshop. All of them is directly output from Rhino. And these are some Dynamo scripts we used. And there's a slight update I haven't put into the presentation, so I'm just verbally going through it. It's financial modeling. So we aim to create profits for both the client and create better socioeconomic values. So here is my brief description. So what if replacing a few properties with green open spaces like a park or lake can generate more profit while improving environmental quality in the surrounding area? So we did this by incorporating the financial modeling data from our client's external consultant, which is KPMG. So they did a brief report with lots of data. Basically, the information will be if your building or certain type of property is close to a urban function like green park or close to hospital, close to waterfront, close to our schools, each of them would have a different revenue uplifting factor applied to them. And again, depending on the distance, and there's also thresholds where it starts, where it stops. So in this screenshot here, we have these buildings enjoying different revenue uplifting factors from, I think, roughly 1% to 10%, maximum 10%. So that will be in these warm vanilla area. And the grayed out enjoys 0% of uplifting because, as you can see, it's not close to anything. We have green park and we have school here and the shopping center, commercial centers. That's why these one enjoy the most uplifting. And again, those data again synchronized into Revit. So that's our way of delivering the actual model with lots of rich information to the client. And this is a example of the report generator. That's a drafty version. So we have this golden column here. The golden column essentially contains value of uplifting percentage. So that's 50.5, 5.5, 2.6. And also each of the building would have its impactors sorted in based on its distance to these urban functions. For example, the building number 4 is closest school, then close to green spaces, and also close to retail centers and also activity centers, and with the relative distance. And this is quite a rigorous mathematical formula being built in. So going through all these sort of calculation, eventually reflecting that sort of like a compiled or combined percentage of uplifting. So the practical usage of that will be basically you drop, just going back to the previous slide. So for example, you drop another park there, and it's going to instantly uplift the values of the surrounding building. Basically, in graphic, it's going to light up the surrounding buildings. And if you demolish, for example, this 6 buildings, create a small park, and you can basically calculate the revenue, and all the revenue is built in as well. So calculate the revenue loss and compare that with the revenue gain by uplifting the original revenue of the remaining buildings. And if the additional gain is actually larger than the loss, that means you can remove those properties, add a new park, creating a better living quality for communities while creating more profits for your client. So that's the end of the presentation, and it's my belief in this computation design stuff is basically it's about design ideas being enabled by computation power. It's not try to sort of compete against the traditional way. It's like I see myself as the assistant to experienced designers. So I try to understand their design logic based on their years of accumulated experience and deconstruct them in more kind of rigorous and rational mathematical formulas and interpret and build all these and run the simulation for them. That's pretty much it. Thanks.